Who's actually going to prove it?
No, that's not the times
All right, so I'm going to interrupt so we can get moving on this.
So it's probably
Okay, we subtract k from both sides. Divide by a. Square rooted. Plus 4 minus. Better than the last. So it doesn't look like a 9. So let's get this taken care of. What do we have? H.
I thought you were going to verify, and I'll do that.
We're good.
We should team teach a class.
Bite.
Just be a matter of time.
get married.
I think you should.
These are some pretty special forms of quadratics. Pretty special, like there's no B term here, there's no term with just an X. Here there's no C term. And here it's written beautifully. We have some number A times this perfectly squared thing plus something else. Because we can undo squares, right? The process is fine. There's really only one other thing we have to deal with.
How hard would it be
Oh.
to take notes if we're both
One's right hand, one's left handed too.
2x squared minus 3x minus 4 equals 0.
I thought we don't know how to solve that yet.
I don't know if we know how to solve that yet. Does this fit the first form? What's A?
2.
And oh great, there isn't even a B in the second one, or in that first guy. So womp womp. The middle one, A is 2, B is -3, but there's a C. So we don't fit that mold. And we certainly don't fit the mold of the last one. So what we want to try to do is generalize what Dave just wrote on the board. Okay. All right, so Dave, you ready?
Been ready, John.
All right.
This last one, you promise not to heckle me now that it's mine.
You're talking to me?
I thought Dead Mass Society was all about heckling.
I know.
Can we heckle you?
Yeah, go ahead, I don't care. So let's go back to the agenda. Notice, of course, we're done with our history lesson. Oh, right, that never happened. We reviewed techniques for familiar quadratics, right? We've got 3 different forms of a quadratic over here. We've been able to solve examples as well as generalize, so that's kind of cool. The next thing we want to do is we want to talk about how geometric models can be useful in discovering algebraic truths. I can look that one myself.
Ooh.
Geometry's kind of cool that way. And then, of course, we're going to talk about how to get that guy over there. Now, let's talk about geometric models. How many of you like to look at pretty pictures? Oh, there you go. That's like 4 of you. This will keep you real good. Maybe I can do sound effects and make it go better. Right. Now, I would maintain that we actually know this already, that using geometric models it can be helpful in developing an understanding of algebra. How many of you have done that in a previous math class? Can you come up with an example of where you've done that in a previous math class? Here, why don't I help? What about a distributive property? You all know a distributive property?
Yes.
Algebraically, what's a distributive property say?
take a number and distribute it across. Yeah, distribute
Right.
it across parentheses.
So what do we do?
So it would be AB plus BC.
Say again?
Plus AC.
AB plus AC, sorry, yeah.
Right, so the A multiplies through AB plus AC.
Yeah.
Right, how many of you look at that and think that is entirely an algebraic thing? How many of you look at that and think that is entirely geometric? How many of you just do it and don't really think much about it at this point? Just checking. John, feel free to chime in, help me out whenever seems appropriate.
You're
So
good.
this is an overhead I used
Sounds
actually back
backward.
in my Math 60 class when we're talking about the distributive property, right? We haven't done a lot of algebra necessarily, but we certainly have a decent understanding of basic geometry. In particular, we understand how area works. The idea behind this geometric model is simply this, that the whole area would have to be equal to the area of that first rectangle on the left-hand side plus the second rectangle on the right-hand side. Does everyone agree that if I were to chop that into two parts and add them, I'd get all the area? Yes, thank you. All right, so let's talk about area of rectangle 1. Chad, why don't you help me out? How would you determine the area of rectangle 1?
3 times 2x.
Outstanding, or
6x.
very good. Keith, can you help me out in determining the area of rectangle 2?
3y.
Right, it's 3 tall and y on the horizontal, so we know that would of course have to be a 3y. That's kind of killer. If we're talking about the whole area, what's the height of the whole thing? 3. What is the width of the entire?
2x.
2x plus y.
Sir?
2x plus 1.
2x plus y. How do you know that?
Because that's the whole top. Part one section of it's 2x, the other one's y, and you have to add them together
Why do you have to add them together?
to get the whole length of it.
One distance plus another distance gives you a
Total.
distance, right?
Yep.
Sure, it's geometric somehow. I think, whatever. Anyway, John, let's just go straight to the quad formula. There you go. That's a way to geometrically, right, attach some physical meaning to what might otherwise look like just a letter pattern, right? Yes?
Yes.
Would everyone agree that the area of that whole big rectangle would be equal to the sum of 4 smaller rectangles?
Yep.
Yes.
All right, now we're doing pretty good. What's the entire width?
A plus b.
And what's the entire height?
C. Either way.
Right, and of course, how would area one, well, I numbered them wrong. Whatever. How do you simplify that? Most of your,
Cross.
you distribute the hell out of it. Right, distribute the A to the C and the D, distribute the B to the C and the D. What do a lot of you call that? A lot of folks refer to that as FOIL, right? First, outside, inside, last. C plus, what do we have? AC we did, AD, plus, there you go, forgive my horrible notation, but most of us have done that before, right? What's the idea?
Like the sum of the whole area.
The idea is that we now have a better understanding of physical representation for something that otherwise is just a pattern. Right? FOIL. Note to self, skip this part.